everybody. Do you like GeeCON? Do you enjoy GeeCON? I hope you do. It's already the second day. I enjoy it too. And today I want to speak about something about Java EE, but more about Reactive and how to make your applications reactive with Java EE APIs. Maybe just I will start with a question. How many of you are using Java EE in your work, in production, pet shop, pet projects? Oh, quite a lot, but not everybody, obviously. Maybe more people use Spring. Oh, I wonder what everybody else uses. Maybe some reactive frameworks already. So another question is the last question. How many of you already know about reactive programming, understand at least the concept, maybe tried some reactive frameworks like Vertex, Ratpack? Oh. Okay, so I won't talk too much about Java EE because I hope that most of you already know, and it's quite boring, to be honest. But I will talk more about reactive programming and how to apply it with Java EE. Java EE should be quite boring. It's just an API we use in our applications. So what's more interesting and what should be impressive is your applications running on top of Java EE. So I hope I will inspire you to put some more reactiveness into your applications, especially when you face some problems and you need to optimize your application and increase the throughput and responsiveness. But first start with what is obvious, what is our daily job when we write enterprise applications. And if we write any other application, we don't care, or we don't expect that will be used too much by too many users. So usually we treat requests, we process requests, we try to gather some data and send it as a response. And usually request processing requires some additional resources that are not in our application. We need to access databases, external services, files, and all these are I/O operations. All these can be blocking. And if a resource is slow, usually external resource is much slower than our CPU or memory. So if the resource is so slow, what do we usually do? Just a question for you. I'll answer it in a minute. We simply wait. And I don't mean it's a bad thing. Actually, in most times, it's quite a good thing because it's that simple to just write blocking code. It's thread safe, so it's quite easy to not run into thread conditions or thread starvation, and is usually enough in most use cases. I don't prefer premature optimizations, so it's not, and I believe for most of the projects, it's not good to prematurely optimize because the additional effort put into optimization will just not be used in production. It doesn't make sense to optimize an application that is going to be accessed by tens or hundreds of users at the same time. You can easily cluster the application just to have two instances instead of one, and that will be enough. But it may happen that sometimes the load is really unexpected and your CPUs are really waiting for external resources, and they can be blocked, and even your application, maybe it doesn't blow up, but it will halt and postpone processing new resources because it waits to finish until the other processing new requests, because it waits until the old requests get processed. So this is all things that may happen if waiting for resources is too long, and you have a classical pipeline, request, response, and send everything when the complete response is ready. Just to stress the keywords here, it's waste. many resources are wasted just by blocking. Every thread has some stack, needs some memory to be running, and if it's waiting, it will just be put aside. Additional context switches between threads are also costly. Not to say that the processing is really slow if your application is not designed to process high load. And it's also good to send feedback to customers if something is happening but it's very slow. But if the application is behaving normally, the response will come to the user, but just at a later time. So it's good to inform users that they should wait, they shouldn't reload because it's an additional request, increasing the number of requests. And in the worst case, they would just forget about your application. If it's public and they don't need to use it, they will just go to another site. And it's also important to treat failures. Again, inform user, recover from failures, recover from long requests, ask user if the application should continue or do something else. So I have lots of experience with Java EE. I even teach some teams about Java EE, how to use it. I'm engineer at Payara server, at Payara project, and at Payara services, which is behind the project. And I'm also a Java blogger, Scrum Master, JCP associate member, and other things like that. But now I want to focus on reactive programming and look together with you what can be done to improve our Java EE applications. We'll start with the reactive manifesto, which always has to be there if someone is talking about reactive programming. It all started with the reactive manifesto. And this is just a short paragraph written by clever people who faced the problem of increasing load, big data, you know, and they invented a way or a design that should help treat the increased load in our modern world. So at the top, you see there's responsive. That's the key word. It's important, as I said, to inform what's going on, to react to failures, to problems, and also to lengthy operations, and send immediately an information to user. It's good if the applications are elastic and resilient, because it means that the applications can consume additional resources to make them faster and responsive to higher and higher loads without rebuilding the applications, without spending too much effort in improving the source code. And if we distribute the application to multiple instances, we also need to treat more and more failures and in network, in the communication between the nodes. So we need to respond to these. That's resilient. And to power all these things together, it's good to have a message-driven architecture so that there are no bottlenecks and no synchronous calls between the components. To explain the idea of how threads can be reused and more effectively utilized with the reactive approach, I'd like to compare what we usually do in our applications with a single-threaded model and what we can do with the reactive approach to improve the utilization of the threads. So on the left side, there is a diagram that explains how in a single-threaded model a thread is utilized. You see there is a request in the beginning. Then there are multiple I/O calls for database to REST services that are outside of our application. And only at the end we send the response. Between the request and the response, the thread is blocked and reserved for our request. So the thread can't process any other request. With reactive approach, the idea is quite different. The application should reserve the thread only when it's doing something. And all I/O calls should be asynchronous. It should be just an impulse, a message that is sent to the operating system or the application server, whatever is outside of application handling these requests. And the application should be notified when the response is ready. And the notification is usually in the form of a callback that is executed on any other thread. It can be the same thread, it can be a different thread, but what's important is that it can be, the thread in between the calls can be used by other requests. In this diagram, we see that the thread number 1 just issues 2 calls. The second call is issued from the other thread. But while the thread 1 is released and the request 1 is still not finished, the same thread can be used for the request 2. And again, send a blocking call and wait for, actually not wait, just declare a callback to be called when the blocking call is finished. So every time a blocking call is triggered and waiting for a response, no thread is blocked and can be reused. In this case, it can be reused by other requests. What's important to realize here is that by this thread model, you can really utilize the threads more effectively. And in fact, if we sum up the work done or the time during which the threads were blocked, these 3 threads can be merged into 1 thread. And that's the idea of saving resources and preventing additional context switches. That if all our code is non-blocking and asynchronous, most of the code can be executed with very small amount of threads. Ideally, the same amount as there are CPU cores, so all threads can be run in parallel and no additional context switches are done to get some more work done. Okay, that was theory. I'll now go to more practical examples. I decided to give a shot with a cargo tracker application, which is already on the internet. It's quite a big application designed by Oracle engineers just to demonstrate all the features of the Java EE API. So you can imagine Java EE is quite a big specification, contains many APIs, and all of them are used in the application. So the application is not like a hello world application. It's quite big. And I try to focus on one single request, which I assume may consume a lot of resources in production, and I'd like to make it more responsive, and optimize it in a reactive way. So I'll just show you what this application is about. It's an application that's used, it's a demo application, so it's not used, but it's designed to have an interface for managing cargoes, which should be delivered from one place to the other place. They need to pass some other places in between, some other ports. They are transferred by a ship, so all the transfer places are ports. But the idea is that someone wants to send a cargo, they get a tracking ID, and with that tracking ID they can use the public interface to see where the cargo actually is and how it's scheduled, what is its route, and when it will be probably delivered. And with the administration interface, the cargo delivery company can manage the routes for a cargo and can update the status of the cargo where it is, and if it's delivered, mark it as claimed. So in our case, I want to improve the page that is behind these node-routed cargoes. When I open it, I deliberately put there some delay between in the computation. But what the page does, it takes quite a long time now. It tries to compute routes, possible routes where with which the cargo can be delivered to the destination. It's not usually possible to find a direct route from one place to the other place. It needs to be transferred to other places, and we have more options because there are already ships scheduled between the places, and we need to find the proper schedules of ships that can deliver the cargo through the other ports to our destination port. So there is a service that computes all the possible routes. With this demo, it's just a random computation, which is just artificially slowed down. But you can imagine there is a very intensive computation requiring much data from database and from external resources. And the service computes possible routes, and we need to pick one of them. So that's this page about. But if the resources are slow, which is simulated by the delay I put into the application, it takes a lot of time to compute it, to even see the page. You see that with a normal approach, you click on the button, you wait, and you don't know if the application just crashed or is stuck somewhere, if the computation is going to be finished. That's a problem. One thing to improve it is to make it more responsive, to give something as a response and computing the background. So let's see what are the options now with Java EE. And the options should apply also to other frameworks which are traditional and use a single-threaded model. But I'm going to use Java EE just as an example. Java EE provides a long list of asynchronous API, which are very essential to build asynchronous processing pipeline and avoid blocking threads. Unfortunately, not all API contains asynchronous API, so we will come back to this later, how we can tackle this problem. So with the asynchronous API, we will come back to our application. We will look into the source code, and we see that this is the pipeline used in our application to process the request. So the request goes through multiple layers until it reaches routing service, which asks an external service called Pathfinder, and that starts the computation of routes. And when the computation is done, when all the routes are computed, they are sent as a JSON response to our main application, and it's transposed onto other DTO objects, added some more information, and transformed to the response. The problem is that the browser sees a feedback or gets a feedback only when it gets the whole response. So let's try to improve it more reactively, to make it more responsive. The idea is not to wait for an external service to finish the computation, but provide some response to the browser immediately, and let the REST service compute and provide data later, and we can pick up the data later and then send this to the same web page, either by WebSocket update or just by polling with an external request. It doesn't matter. I used WebSocket updates, which already uses the idea of asynchronous messages. So let's go to the details and see an example of how the code looks like with adding asynchronous API to our JAX request call. I'm not going to type it because the code is quite horrible. We will improve it into the next step. But just to show you the idea, First, we had normal blocking GET call to our REST service. So we issued GET call from a normal blocking Jaxara's API, and the GET call only accepts type of the response. We don't need to put it if we just want to handle the generic response type, but if we wanted to convert it into our business type, we can provide the type, which is in this case list of transit paths. And that's it. This get method is blocking and waiting for the call to come back from the REST service. And when it's back, it's transformed to our list of transit path objects and then processed in the application and transformed to the response. With asynchronous call, we can provide a callback to a get method. And actually, Jaxara makes it quite straightforward. It only provides additional async call to the Fluent API, which gives you a different interface, which has the same method that the original interface, but the methods now are able to accept more arguments. And the really asynchronous methods, really usable for our reactive programming, accept callbacks. There are also some variations which return future, but future doesn't prevent blocking, because to get the result from a future, you still need to keep the original thread and wait until the operation finishes. With the callback, you don't need to keep the thread. The thread will be created or reused for you by the application server with the invocation of the callback. But that's the idea. You see that the code is quite horrible to read. Actually, the business logic stayed there, but there is lots of boilerplate. So let's improve it. We can improve it much more to make it much more readable with chaining callbacks. Actually with completable future or any other library which is capable of chaining callbacks, using a promise pattern. You may know promises from JavaScript. The idea is to avoid nested callbacks, because if the callback is called and it needs to do some operation, everything needs to be done in the callback. And if it runs additional asynchronous call, it needs to provide another callback. So there is chaining of callbacks, and with normal approach, normal syntax, you would nest callbacks into callbacks into callbacks, and the code would look like even much more worse than what I show you. But with using completable future, we can use Fluent API and lambdas to chain callbacks. Every callback will be a lambda, and it will be sequentially added to the completable future, so it's more readable and more reusable. You can also use other third-party libraries like RxJava observables, which are even more convenient when writing reactive code, because you can process multiple pieces of response in a stream. But it's also possible with compilable future, but it's not straightforward, so I recommend to use RxJava. I'm using only Java 8, so I decided to use compilable future even for that. And completable future is an object, is an implementation of completion stage interface. So completion stage provides methods to chain callbacks. Completable future is only used in the method invocation when the computation is finished. So to show you how the code gets better, with using completable future, we can have almost the same code as we had before. We only use async method of JAX-RS to turn the interface into the asynchronous interface. And we can create a very simple wrapper that maps the callbacks into completable future and wrap any call in the interface that is asynchronous to make it return a completable future. So we need to transform the callback which we pass as an argument to make it a return value. That's very easy with JAX-RS with this. It's only necessary to do something like this. This is actually much more complex because I made it more generic, but the idea is to have something like this. We only implement the invocation callback. We can also extend completable future because it's a non-final object. We can also embed the completable future inside and return it from a method. I thought it's more convenient to extend it. And the thing is that when the callback is called, either completed or the failed method is just transformed to the call to the completable future, and the completable future is returned from the call. The call isn't finished when called, isn't blocked, but when it's finished, the completable future is finished, and then the callback is executed with the then apply method. So this is the only thing you need to do, except also turning the return value into completion stage. And then when you change the interface, you also need to propagate a completion stage to the additional layers, just up to the page you process, up to the JSF code in this case. So it's kind of more work to do, but it's only changing of the interfaces and changing one lines of code in each component to turn it into asynchronous processing. Every call should then be executed asynchronously, because otherwise you need to still keep the original thread and wait until the asynchronous execution completes. So with this approach, I'll build the application. Actually, I'm not sure if we already improved the UI. Let's see. No. We only improved the call. We still didn't come to the UI. We didn't apply everything up to the UI, so the UI is still waiting for the asynchronous call to finish. This is what you get if you only improve the component at the bottom and don't fix the components at the top. So let's now improve this with messages. And the first thing to consider when we want to improve the UI to make it responsive is to somehow update the UI asynchronously. In this case, I am using WebSocket. You can also do some polling, and it's also basically messaging, but using a polling mechanism. The browser needs to ask about any other data regularly. But with WebSocket, you don't need to do that. The browser just opens a WebSocket channel and receives messages from the server. So once we do it, we will improve the application in this way. I'll just build it in the background and show you the code meantime. Initially, we had a model for our page, which provides all the data, and when the data is prepared, the page is rendered, getting the data from the model and displaying it as a HTML page. But for updating the page asynchronously, we need to first send some initial data to the page, so we need to modify the HTML to contain only the data which is computed very fast, and then update the UI with additional data. So I'm using Omniface's push context, which simplifies working with WebSocket with Java EE, but you can use also plain Java EE API. And the changes here, it's not very big. Here is some code that initialize some data. And here is code which works with the browser to set up the initial WebSocket connection and wait until the WebSocket connection is initialized. Because now you have two options. Either WebSocket is initialized before you have additional data, or additional data is computed before WebSocket channel is initialized. So you need to wait and synchronize. I'm using completable future to do this. But the real work is here. When we request computation of the new routes, we return completable future. So I already changed all the components below to return a completable future. I get a list of candidates, and now I can change a callback to send these candidates, or I'm just actually sending an update request to the UI so that it gets the candidates from the JSF model. But if you're using only plain JavaScript framework, you would just send all the data and process it in JavaScript. And in the end, I will either send error if an error occurs, so if the completable future completes exceptionally, or I will send finished so that the UI can stop refreshing. So I'll deploy the application now. It's getting deployed, yes. And now the application changed. You see, we have response immediately, but the page is still waiting for the responses, and it's still waiting for too long until all the data is computed. And when it's computed, the page is updated and the progress bar is gone. Better, but it can be improved even more, with even more messages. Oh, sorry. We can use any messaging mechanism to connect our main application with our Pathfinder component, which computes the data. But the essential thing is that the component which computes data doesn't send it in a big chunk, but in smaller chunks. So the application doesn't have to wait until all the data is computed, but receives the data at the time they are computed. So in this case, we want to receive root candidates immediately when they are computed, and then again and again to update the UI one by one. We can use JMS, which is quite cumbersome, but is already in Java EE and ready to use. If you're used to it, there's no problem with that. But we can also use CDI events if the communication is not critical. We don't need transactions there, and we really want to keep it simple. One thing with CDI events is that they only work within the Java virtual machine. So they are not true messages, they are only events received by our application. But we can easily extend them to be transferred to other virtual machines. Later we will see how. So now the diagram of our application changed a bit. at the bottom. We no longer want to wait for all the data computed, but we send a message and forget. We will again return what we have, but then the Pathfinder component computes the messages, computes the data, and for every root candidate it sends a message. So we receive multiple root messages. For each message, the components that are between the page and Pathfinder send the message, route the message to the top component itinerary, and it sends the data via the WebSocket to the page. And at the end, just to make sure that the page knows that no data will come, we send a finished message. This is just an implementation decision. You can also send some information in the last message. It depends. So I'll just build the application again and show you the code first. Not interesting. What is interesting is here. We no longer issue a REST request, because REST request is always fire and or request response, not fire. Forget request and response. It needs to wait until response. And if the response, we could turn REST request into asynchronous if the request is finished immediately, but then we need additional channel to send the data. So there's no really point in using REST for this. We can use the same mechanism as for the data to start the computation. So to do this with CDI, we would fire an event. To wrap this code, this logic, which is not interesting, it actually isn't logic, it's a boilerplate code. I created a resource around our service, and the resource sends the event and observes the events so that we can, again, chain callbacks to our invocation. And to fire event, we use normal CDI events. For those who don't know CDI events, those are objects provided by the application server that can be injected into your code, and you can just use them. It's an interface that makes it possible to fire an event and with any payload you want. So in this case, we fire an event with is marked as outbound, which is a special qualifier to mark it to be serialized and transferred to any instance in the cluster anywhere through the message bus. And on the other side, we receive events just observing them, which is the other part of the CDI API. If you declare a method with observes annotation that can consume the message payload, it will be triggered by the CDI or by the application server when the message is fired. To make it listening on these serialized events, we need to mark it with inbound. And just to explain, these inbound and outbound qualifiers are not standard annotations. I'm using the annotations provided by Pyra server, which is an application server. But it's quite easy to create your own annotations like this. You just need to wrap a mechanism that is capable of transferring messages, transferring serialized objects to other instances, and create an observer for this outbound event, which is able to send the messages through this messaging solution, and on the other side, handle these messages or get these messages from, e.g., Hazelcast. Payara uses Hazelcast there, but you can use any other clustering mechanism or any other mechanism that is able to send messages across the network. And your application would need to raise another event, which is in Payara server called inbound, so that applications can observe these events. So you just put something in between the events. You don't handle them in a normal way, but intercept them, send them to other machine, and you can listen to them somewhere else. This is important to make your application elastic, which is one of those blue boxes I showed you before, so that you can scale easily just by adding more and more instances without putting too much CPU resources on the same machine, on the same application, without redesigning your application. You can just send the messages to many listeners, and either those listeners, all of them, pick the messages and add something to the computation and start sending messages back, or you can synchronize and make, by creating a simple load balancer, so that each message which starts a computation is picked only by one instance. And then another request will send another message, and it will get picked by another instance, so you can easily load balance with messaging. So I'll show you the application now. And what we got is, now it looks like the same, but we are receiving root candidates one by one and updating the UI, and still computing 8 candidates. Wow, this time. It's completely random, so I don't know how many it will be each time. But after receiving all the candidates, the progress bar is finished, and the page is rendered. Essentially, it should be the same page as we had in the beginning, but more responsive in a more reactive way in the backend. We can improve the processing on the backend when the code is more reactive by playing with threads, optimizing the code, or just put more instances into the cluster so that the application scales without any changes in the code. To show you what's possible once we have this distributed event bus, I'll show you one feature of Payara server, which is called Payara Micro. It's actually a distribution of the server that can be run just from command line. It's a jar file which is 60 megabytes big. It contains lots of Java EE API, and you can run it from command line with -jar, deploy any applications on it, specify command line options, and just run it. Forgot to change the folder. You can even bundle your applications as a standalone jar. It's just, I don't want to bore you with Payara Micro, but just, I think it's quite cool to show. Let's name it Payara or app jar. And it will bundle everything, the command line options, the runtime of your application into an executable jar, which you can just execute with like this. And it would be the same as if you executed the previous command which I had before. If we have a proper server in the cluster, we can also see all the Payara Micro instances that joined the cluster. Right now we have, I started a micro instance even before. So we have now 3 instances of Payara Micro, which are smaller application servers, and one big application server with administration console, which can even send commands to these smallest biomicro instances. So let's list applications. In them, if we issue a command, it will send it across the cluster to the instance, receive the output, and display on the console. So we can be sure now that the Pathfinder application is deployed in our biomicro instances. And to show the effect, let's go to the page again. And now we see that all the instances are computing the responses or the data. So we get data much faster. Of course, this is just a demo. Maybe you don't want to work the application this way, but it demonstrates how easy it's to spread the computation across instances just by adding more instances onto the cluster. You can improve this behavior by synchronizing the services, e.g. via JCache. JCache is a caching API which is also provided by parent server, also provided by Hazelcast. So even if you build your own extension over CDI events, if you build it on Hazelcast, you can use Hazelcast to synchronize with distributed logs, and you can ensure that the additional instances will load balance the requests. Two more things I want to talk about just quickly because I'm running out of time is that when it's not always possible to write asynchronous code, it's not always possible to get rid of blocking tasks. So we need to handle the code that is blocking. We need to avoid any blocking call in our asynchronous responsive chain because it was just block threads. And the idea with reactive programming is to reduce the amount of threads as much as possible so that thread contexts are not very frequent because they are costly and they don't do anything except of just changing the workers. But if we reduce the amount of threads in the original thread pool, and we forget about some blocking calls, they can completely stuck the thread pool very easily. As you saw the animation in the beginning, if we have less dancers will perform, and maybe even no dancer will perform. So, but if we have many threads, many dancers, we can still have some free to do the task. So what we can do is to introduce more thread pools and have a thread pool specialized into blocking calls, which can be which can contain much more threads. But these threads won't be frequently used, and they will be used only for blocking calls. So there's no much additional cost in the thread in switching between these threads because they will be blocking. It's the most costly operation, a blocking call. Then context switches are very not much expensive compared to that. So in Java EE, you can easily create a separate executor from even your application. You can define executors in the application server, but you can also define executors in the web XML. This one. Defining executors is as simple as this. You just give it a JNDI name and define the type of the executor, which is always the same. And you can access the executor by specifying this JNDI name. So normally you would use the default executor, which really needs to be there in the application server, but you can add more executors to separate the thread pools. And every blocking call should be called in a different thread pool than the non-blocking call. And the final thing is context propagation. It means that when you need to jump from one thread to another thread, as opposed to the traditional model where you reuse one single thread for all processing, you need to conserve the context and send it to another thread. Because you don't know if the same thread will be reused or if the callback will be executed in a different thread. So it's important to remember to conserve everything. Some things are propagated automatically or intuitively. For example, if you have asynchronous response object with asynchronous GeeCON API, you process a request, but you, instead of processing it in one method, you define the method as asynchronous. You receive an object which contains the context of the response as an argument to a method via injection, and then you can finalize the request by this object. For some other things, it's not that easy. They are bound to a thread, so you need to transfer them, usually using context service that is capable of conserving the state from one thread and move it into another thread. I don't have time to show the demo, but there are some more slides that can hint to how to do this. Some things are not that easy. For example, transactions, because they are naturally bound to a thread and it's not easy to move them to another thread. But you can use non-standard transaction manager, which should be in every application, or can be in every application server, and it really is in most servers, but it's not mandated by the specification. So if you are running with a really unusual application server, you may not have access to transaction manager. But transaction manager is capable of suspending a transaction and resuming the transaction in a new thread. And with CDI, it's also problematic because some very frequently used CDI scopes are also bound to a thread. For example, request scope or session scope. They are not normally available in another thread, or even if they are not the same. So it won't be the same request scope in one thread or in another thread. You would get different objects if they are request scoped. You can use Microscoped project, which is just a small CDI extension on GitHub to define your own scopes when they should be started when the request is started, but not finalized when the method is finished, but when all the processing is finished. So you see, reactive programming is not so easy, and those are my final words. I recommend looking into experimenting with a reactive approach, but don't apply it in every part of your application because you may suffer. It's maybe better to look at other frameworks which are reactive from the bottom, which only basically are built to support reactive programming and to get inspiration from that. For new projects, maybe Java EE is not the best tool, but most of you are probably stuck with your own existing projects, so I hope you get some inspirations from this talk to improve your applications. I don't have much time for questions, so thank you everybody for joining my talk and enjoy the rest of the conference.